Hello and welcome to this new tutorial, and welcome again to step 9 on reinforcement learning. So now that you've just seen the intuition lecture with Kirill to understand what reinforcement learning is about, well, we will implement some what we call pseudocode so that we can understand where reinforcement learning comes into play in this full world model. Meaning we're basically going to implement a very simplified code that will follow all the steps of the process happening in the full world model from start to finish, from the first observations, which are the very first inputs going to the CNN, then the VAE, which returns the latent vector Z, which will become the input of the controller, also taking the hidden state as a second input. Then this controller will return the action to go inside the environment to get the reward, but also to go back into the MDN RNN, because remember that the MDN RNN actually takes three inputs: the action, the previous hidden state, and the latent vector Z. So we will recap all that into a code. This will not be the real and final code of the full world model, which we will execute in the end to, race against our AI, but it's important to still implement that pseudocode so that we can not only really understand the process of the full world model, but also put what you've learned about reinforcement learning into practice. All right, so let's do this. And just before we start this pseudo implementation, I would just like to remind that the controller, right here in the full world model, is actually a simple linear matrix. It's a simple single layer linear model, which is exactly that matrix here, WC, which takes obviously as input Z and H, that we can see here clearly, and which will return as output the action. And it's really, really important that you understand this, that the controller is actually a simple matrix, therefore of several weights or several parameters, because then in step 10, we will start to learn about genetic algorithms and evolution strategies, which will exactly optimize the parameters inside this control matrix in order to maximize the cumulative reward. And speaking of the cumulative reward, well, we will include that in the pseudocode. That's really part of the process here. It is actually what's happening here. Once the action is played by the controller, well, we get a reward inside the environment, depending of course on the score that you saw in the very first tutorial of this course. Basically, the faster the car goes and the further it gets along the road, the higher will be the score, and therefore the higher will be the cumulative reward along one episode. And that reward is important because that's exactly what we need to optimize and maximize thanks to the deep neuroevolution strategies in step 10. So we will basically implement in that pseudocode everything to be ready for step 10, and also, of course, to put what you've learned about reinforcement learning into practice. All right, so let's do this. Let's go back to Python and let's implement the whole full world model process, of course, very simplified. All right, so we're going to start from the very beginning. That's why I've put the whole process of the full world model just next to my code. And so the very first step is, of course, when the input frames come into the CNN VAE, right? Remember that we implemented the CNN plus the VAE in the same card, and we call that a conv VAE. And so that's, of course, the first step of the process. But before we start, this loop that will basically loop over all the iterations happening in one game, exactly this game that we and the AI played at the very first tutorial of this course, well, we have to reset everything. We have to reset the environment. We have to get the initial state. We have to set done to false. There is always a done in a reinforcement learning environment, and it says whether the game is over or not. Done equals true means that the game is over, the race is over, and done equals false means that the game still continues, like we're still racing. And of course, before we start the loop, we have to initialize the cumulative reward to 0. Right? I told you about the cumulative reward. It is at the very beginning, just before the race starts, initialized to 0. And then at each iteration, we're going to increment it by the reward got at a very specific step of the environment, meaning when the controller plays an action. All right, so let's do all these initializations, starting with the environment. So usually when you work with a reinforcement learning environment like the car racing game, which is a pre-built-in environment, I think, by OpenAI Gym, well, the developers of such environments always implement a reset method, which not only resets the environment, but also returns the first image or observation of the game. So, that's the very starting point of the race. And so that's our first step here, and therefore I'm going to introduce a new variable which we're going to call ups, and that's exactly the real frame that the agent will see in reality, therefore before the dream. And so ups will get that first observation or first input frame by calling the reset method from the environment object of the car racing game. And so to call a method from an environment object, env here is an object of the car racing game environment, well, we add a dot and we call that method reset with some parentheses. All right, so you will see that all the time playing with OpenAI Gym environments. Then, what did we say? The second thing we need to initialize here is, of course, the initial state of the MDN RNN, right? Remember that in the MDN RNN, and especially in the RNN, we not only have the output Z of the RNN, but also the hidden state. I've prepared that for you actually right here, just as a quick reminder, right? You can see that the RNN takes as input 3 elements: the previous hidden state, the previous action played, and the previous latent vector Z, and returns as output, well, first the deterministic output of the RNN, and of course the hidden state. And what we have to initialize here is the first hidden state which will come into the RNN. And remember that we actually had a parameter for that when we implemented the RNN. It was, I think, called the initial state. So that's exactly what we have to initialize right now. And so we're going to call that H. And if we go to our RNN implementation, well, that's exactly what we introduced here as an object variable of the RNN. This, by the way, will be, of course, part of the real final implementation. This is just some pseudocode, but what you have here are the real variables, of course, of the whole implementation. All right, and so back in our reinforcement learning pseudo implementation, well, since the initial state, this object variable that we created here comes from the build model method of the MDN RNN class, well, we will simply call it this way so that everybody can understand. We're going to take an MDN RNN object of that same MDN RNN class, from which we're going to get the initial state object variable, exactly this one, right? It doesn't really matter here at this stage which format to take exactly, but at least this way everybody will understand that this is indeed an object variable, the initial state of the MDN RNN object of the MDN RNN class. All right, so that initializes the initial state. Then, very important, when you're iterating on an episode, or also called a rollout of a reinforcement learning environment, you always have to initialize first the done variable, which is always one of the 4 variables in each and every step of the environment, which are, let's remind them, the current state, the action played, the reward received, and this done variable, telling whether or not the game is over. And of course, when we're starting the game, because right now we're initializing everything before we start the big loop of the game or of the race, well, done will be equal, of course, to false, because the game is about to start, it is not finished yet. So done equals false, and then finally, very important as well, especially for what we will do in step 10 to maximize or optimize the cumulative reward by finding the optimal parameters of the controller, in that matrix WC that I've showed you before. Well, compulsory step as well, we have to initialize the cumulative reward to 0. And now we can start the loop. We can start the whole loop of the game. So this whole loop will be a single episode of the AI racing its car in the environment. So since we have the done variable, well, the simplest way to implement that loop is with a while, while not done, meaning while the game is not done, while we're not finished racing our cars, well, what will happen? Well, here, that's when things start to get interesting, because that's from this point, we will follow exactly the path of the full world model. So we're going to start from the very beginning, from here, when we get the input frames from the game of our car racing in the car racing environment, and then following all this path while not forgetting any of the loops here, until the final step of the path when we reach the next state in the environment, and then here again the process starts again. Alright, so the very first step is to get the input frame. Then the input frames goes into the VAE, which returns the latent vector z. And so what we will simply do here is, since we've already initialized the observation, meaning we got the first observation, well, we can directly get the output of the VAE, that latent vector z. And then, later on in the loop, we will update the observation once we reach the final step of the process. But first, we have to get that z, that latent vector z. So what I'm going to get here, the next step, is to get that latent vector z, which will be returned by the VAE. And remember, in the VAE, we called our class conVAE. So let's say that the object of this class, which we will create later on to use that part of the full world model with the conVAE, well, let's say that this object is called CNNVAE or conVAE, as you prefer. And so the CNNVAE, let's simply write that it takes as input, as we can clearly see here, well, the observation. The observation, which was initialized in a variable, the ups variable. And therefore here, we simply input ups. Alright, so that's the first step, getting the observation. It goes into the CNNVAE, which returns the latent vector z. Great. And now, next step. What is the next step after we get the latent vector z? Well, very simply, the latent vector z is propagated up to the controller, which takes it as input, but which also takes the hidden state. The hidden state that we already have because we initialized it in the initialization step. And therefore, we're going to get it now with our other input z. Therefore, we're ready to call the controller, and we're ready to get the action returned by the controller, which will go into the environment. So let's do this. Let's get our action, which we're going to call A. And now let's call our controller, which will of course be created later on in the implementation. And as we can clearly see on the article, well, it takes as input that horizontal input vector zt and ht, the current latent vector z, the last one got, and the current hidden state h. So make sure to not confuse that with a product. This is just a horizontal vector, and the reason why I say horizontal vector is because we're doing here, again, a matrix multiplication. This is a simple two-dimensional matrix, which will be multiplied, as in a matrix multiplication, by this vector composed of zt and ht. And so that's exactly what we're going to pseudo implement right now. We will put these two vectors into a concatenated one-dimensional input vector, as it is said here, the concatenated input vector zt, ht. And therefore, to simply write this, we're going to add in some parentheses here that concatenated vector into square brackets, and we will just input here z and h, right? So basically, that means that the controller takes that concatenated input vector composed of, as we can clearly see here, the latent vector z and the hidden state h, which we both have because we initialized the hidden state h and we just got the latent vector z. So we're ready to call the controller with those two elements to get the action. Alright, and that's the next step. And now let's see the next thing we have to do. Well, very interestingly, that's the missing part of the full world model, which we haven't covered yet, and which is really the step where reinforcement learning comes into play, because that's now that we're going to call our environment, that environment object of the car racing game class, fully built by OpenAI Gym, because our environment, as for any environment of any games in OpenAI Gym, has this method that we call step, and which is exactly the method taking as input the action that was just played to return three very important elements, the three elements of a step of a reinforcement learning environment, which are first the next state, so the next observation happening in the game, and therefore the next input frame to go again into the full process. Then the second element is, of course, the reward, the single reward received at this specific iteration, but which will be incremented into the total cumulative reward. And the third element, of course, done, telling us if the game has stopped. So for the car racing game, done will only be equal to true when it's the end of the game, when we have reached the 30 seconds. But sometimes for some games, well, the game can finish before. All right, and so that's exactly what we're about to do. We're about to call this step method from the environment, which I remind once again is a pre-built method by the OpenAI gym environments, but it is always called step. And therefore, let's get it. This step method returns, as we said, the three essential elements of a reinforcement learning environment, which are first the next state, but which we're going to call ups, because it is simply the next observation of the game, and therefore we're updating our ups variable, which will become the new observation basically. Then, of course, the reward obtained at that specific iteration, and then done, telling us whether or not the game is over, that is, for our case, the car racing game, whether or not we have reached the final 30 seconds. All right, and so these three essential elements, well, we will get them by calling our environment, that same here, but this time we're not going to call the reset method, we're going to call, as we said, the step method, which takes as argument, well, exactly that action played here by the controller. And therefore, since we have it here, since we got it by calling the controller with our two elements, the latent vector z and the hidden state h, well, we can simply input here this last action played A. All right, and perfect. And so now the next step is very natural. Since we got the reward at that specific iteration, well, we can update the cumulative reward by incrementing it by that reward we've just got in that specific iteration. And so here, what we're going to do is update it by incrementing it by that reward just obtained. And now there is a final step we must not forget. We have initialized the initial state of the MDN RNN, but at no time have we updated it in that while loop, that loop iterating on the whole game, the whole race. And so we have to indeed get the next hidden state, which is exactly what's happening here, There is a loop here, right? After the MDN RNN returns the hidden state, well, that hidden state is taken back to the MDN RNN along with the last action played. That's exactly what we see here in the MDN RNN part of the article, right? We clearly see here the previous hidden state, which comes from the retro loop of the RNN, which you saw in the intuition lecture, right? And so what we have to do now, the last step, before we make this game loop complete, is to update the hidden state h, or to get the next hidden state. And therefore to do it, well, we're going to call again our MDN RNN object from the MDN RNN class, which we built in, well, step 8. So we're going to call that object, and very simply we're going to take as input the three inputs of the MDN RNN, which are the previous hidden state, the last action played, and the previous latent vector z, to return that next hidden state. And therefore, to write that simply, well, we're going to update the hidden state h by calling again our MDN RNN object, which we already introduced here, MDN RNN object of the MDN RNN class, which will take as input, this time, a concatenated vector of three elements, which are, as we've just said, the last action played, right? That's the last action played. Then the last latent vector z, which is exactly this one, z. And finally, the last hidden state, which at the first iteration of this while loop is the initial state h. But then at the second iteration and the next ones, it will be, of course, the previous hidden state h of the previous iteration. And perfect. This is how works a reinforcement learning environment for the full world model.